here. I have a test written, and I can now try and develop the max function. We're going to try and develop it from scratch. So the way I suggest you do this is to start working with an example. So let's work with this example where we have 21, 41, 31, 51, 11. And I suggest that you start sort of in the middle of the process of determining whatever you want to do in this loop. So let's suppose we've already looked at the first three characters and we're just looking at the fourth one, which is 51 here. Now, if my loop has already gone through the first three, I need to have determined stuff about the first three in order to know what to do now that I'm seeing the fourth one. And so the process of designing an algorithm here or a loop is to think about what you need to know in order to make progress. So one thing I could certainly determine is the maximum number of the previous three. So if I know the max of the previous three, then by just looking at the next number, I can compare this number to the previous max, and I'm good to go. That's sort of the way the algorithm we had worked. So, I mean, one thing is I do need to know where I am. So there needs to be some sort of marker to say, oh, currently I'm on the fourth element, which is index 3. So I need something. The typical name for this is I. So that's for index. So that's my index into the array. So in this case, I would be 3, telling me where I am. And so what I'm actually doing here then is I'm comparing the element at index I. So that's written A of I. And I'm going to compare it to m. So I'm comparing these two things. Oh, wait, what's m? So m, So I need to know the max of all the things I've looked at so far. So at this point, the max would be what, 41? So I need to know what was the max so far. So there needs to be something to hold that. So let's call that m. Okay, and so what I'm doing is I'm comparing the max so far. So if the max so far is less than A of I, then I want to update the max so that it is A of I. Yep, so like yay. Getting used to the syntax of Java may take you a little while. You'll get used to it. You just need to know where the semicolons and the curly braces go. Okay, so this is the line that actually makes us progress then. So that's great. This will actually look at 51 then and compare it to 41, the previous max, and update the max to be 51. At this point, I have actually looked at A of I, and therefore it's important to make progress. I'm going to update I as well. So we'll increment I by 1. There's lots of ways of writing this in Java. You can write it as I plus equals 1 or just I plus plus. These all do the same thing. All right, so there I have made the body of my loop. All right, so where do I stop? Well, it's important I don't look at A of A dot length, because that is beyond the end of the array, and I'll get an exception if I try to do that. So it's important that I stop when I is equal to A dot length. So I'll continue as long as I is properly less than A dot length. Okay? So now we just need to figure out what these values are. And well, for the value of m, I'm going to assume that the array has at least one element. So we'll take that to be A of 0. And note that I've already looked at A of 0, so I don't need to look at it again. So I'll start I at 1. In fact, so it might be better, this is just fussing around, but so it might be better to write it this way. So m is A of 0. And now I know that I've already seen 0, so I don't need to start there. I'll start with 1 and continue. If you were to write your code like this, where you're actually looking at 0 twice, it would work, but it would confuse anyone who tried to read your code. So unnecessary work is always bad. Not so much because it takes more time or anything like that. It just makes the code harder to understand. So if you're doing something like this, someone who's reading your work would be like, really, do you need to do that? You know, why? And so they're going to have a question about it. Whereas if you write it where you're doing only the work necessary, then any reader will immediately understand what you're doing, and they won't be questioning, you know, what is going on in the code. Okay, so there you go. So that's this code in a while loop. So once you've gotten this all settled down and it looks like it's going to work, you need to worry about corner cases. So corner cases are things like empty array. So what if somebody gives me an empty array? Well, poo. I'm not going to be able to work with that. So what I'm going to do in that case is I'm going to throw an exception. New illegal argument exception. There we go. Okay. So that's fine. One thing you'll note is that curly braces are optional in Java for single statements. So I don't actually need a curly brace here. It's not a bad idea to put it in though. So they're not required if you only have one statement inside your if. If you're ever confused about what exactly you think your code is doing, it's always handy to try and format it and see what Eclipse thinks it's doing. You see, Eclipse will actually spread out the curly braces and everything in a certain style. And you can make sure it sort of corresponds with what you think is going on. Okay, so this is nice. There I have a function, and we sort of derived it. And this is indeed the code if you want to see the while loop version of this. Using a while loop or for loop doesn't matter. It's exactly the same. So while loops and for loops in Java are interchangeable. All right, so let's just talk generally about what we just did. So whenever you want to design a loop, what you want to do is pick an example and start in the middle. I think this is the most important thing. Don't start at the beginning, don't start at the end, start in the middle. Assume you've gotten some way through the array, and now you need to make one step of progress. So in order to figure out how to make a step of progress, you're going to have to look and figure out what you need to know. So you almost always need to know where you are, and you need to know something about the things you've looked at. So in this case, we're keeping track of the maximum of the things I've looked at. And so at each step, I'm just looking at a new value and seeing if it's bigger than that previously computed maximum. And so this will tell you what variables you need. So in this case, in addition to the index I need a double M to keep track of the previous max. So once you have that, you can sort of write the body of the loop out. And then you can sort of figure out how it's going to end. So like, where do I stop? And then you figure out how to start everything up, get the initial values, and then you deal with these corner cases. Okay, so whatever they are. One common mistake of beginning programmers is to think that variables always need to start at 0. It's just not true, so don't do it. Starting at 1 often makes a lot of sense. So starting at 2 might make sense depending on your application. Okay, so it's not always going to be 0, your initial value. All right, so that's a general way for designing loops. There's actually many different ways we could compute the max. So I've given you one. It's not the only possible solution. There's other things we could do. So let's think about one of them. I'll just leave this in here because that takes care of this case. But let's suppose that instead of doing things this way, actually let me just get rid of all this stuff. There we go. So, oh, by the way, I need to return the, in the previous code, right, I need to return the max that I computed, not 1. That my test would catch that for me. Okay, so let's think about a different approach. So what I'm going to say is, all right, let's suppose that instead of knowing the max so far, I don't actually know that, but I do know that none of the numbers I've looked at so far were the max. So when I look at this number then, I just need to see, is it the max? And if it is, I can return it. Yay. If it's not, then I just skip it and go on to the next one. All right, so in this case, you end up with a very different bit of code. So in this case, what I need to do, well, just to refresh your memory, so before what we were saying is if m is less than a of I, then I was going to set m to be a of I. Right, that's how we were making progress last time. What I'm going to do here instead is to say, oh, okay, well, if none of the previous numbers were the max, then how do I find out whether or not this number is the max? Well, it's pretty straightforward. So let's suppose I'm at the ith number. All right, I'm at number I. And what I want to do then is check a of I. And I just want to see if any number in the array is bigger than a of I. If any number in the array is bigger than a of I, then I didn't find the max. Okay, so how do we do something like that? Well, we have to go through the whole array. So let's use another variable. We'll call it j to go through the array. And to go through the array, it's always kind of the same process, right? Here starting from 0 up to a of I minus 1, the length minus 1. And I'm going to increment j. Okay, so for all of the elements of the array, what do I do? Well, I'm going to see if a of I is, if a of I is smaller than any element of the array, then if it's smaller than a of j, then what am I going to do? Well, I know it's not the max. Well, what am I going to do with that knowledge? I think I need a variable. So let's create a Boolean, something like is max. Initially, we'll say it's true. Okay, so we'll assume that I am the max. And now if I see something bigger than a of I, then I'll say, well, is max is false. Okay, there we go. That should work, something like that. And then after I've gone through there, I can say if is max is true, then I found the max. So I can just return it at that point. I don't need to keep going. I can return a of I. That would be the new max. Okay. Oh, okay, this is interesting. So we need to do this for every I. And so what we're going to do is do this for, what, I from 0 up to I minus, right, up to the length. There we go. So we'll do that for every I. The indentation's gone all wackadoodle. So let's get rid of this declaration. We don't need that. And now let's indent. Oops. Okay. We're starting to look good. And I think, yeah, we're almost making sense. Okay, so let's see. So for any I, so I is going from 0 up through, all the indices, we are going to look to see if a of I is the max. So how do we know if a of I is the max? Well, we'll start off assuming that it is. And if we see anybody bigger, then we'll assume if we failed. Okay? And so if after looking at all the other elements, we know that this is the max, then we're good. So we know it is the max. So we just do this for every element. So we end up with this awkward little error here, though, in Java, which is it's saying that you need to return something here. It's actually impossible for it to get to this point and ever in a program. So as it turns out here, if you think about it, if the length was 0, we've already thrown an exception on line 7. Otherwise, let's suppose we just have a single element. Well, it'll never be properly greater than itself, and so our single element would be the max. Okay. So one thing we can do is just say, well, we can do all this work here, and then we can move this. The error is coming because Java is not smart enough to figure out that you can never get to line 14. So in any case, we can just reverse this so that we go ahead and do this loop at the top. Note that if the length is 0, this body will never execute, and we'll just immediately throw an exception. So it's equivalent code. Does it work? Let's try. See if we got it right. Yeah. Okay, cool. So this is another way of doing the max. And some people would argue this is clear. They're like, yeah, this makes sense to me. I get it. So what I'm doing is just looking at each element and determining whether or not it's the max. And there's a question of like, okay, that's fine. I mean, is this as good as the other solution? Is one better than the other? There's not an obvious aesthetic reason, perhaps. I mean, some people might say, the problem with aesthetics is beauty is in the eye of the beholder. So simplicity, which one is simpler? I don't know. Some people do think about the problem differently. And so sometimes you can make an argument that, this way of thinking about it made sense. We're just going through and we're checking each element to see if it's the max, and we eventually find one. So what's wrong with that solution? Seems fine. So, but in fact, these solutions are not of equal quality. And to understand this, we need to actually think about how long they take to accomplish what they're doing. So I'm going to use a different solution. So we saw that this is correct. So both these solutions are correct. I'm not going to look at them in terms of correctness, and I'm not going to look at them in terms of understandability. Both solutions are understandable, but they have very different performance characteristics. So let me first try the initial solution. So this is my solution that we had initially using a while loop. So here we're just im is aggregating the max so far. And if you run this, what I'm going to do is run it. And I'm going to run it many times, okay? But I'm not going to run it on small arrays. I want to run them on fairly large arrays. So my main program here is going to start at a minimum size of 1,000. And we're going to go up to about 1 billion if we get there. So this is the underscore in numbers just makes them a little more readable. That's 1 billion, that's 1,000. And my main program then is going to start a trial, passing in the size. And then it's going to run a loop where it starts with a 2,000 sized array, going up to the max, up to 1 billion. And each time we're going to be doubling in. So in is doubled. And what we're going to do is run the time trial again with a double-sized array. We just keep doing this with bigger and bigger and bigger arrays. And what I'm going to do is just measure how long it takes to run the max function on an array of that size. So to get an array of that size, I'm using a class that's in your standard library. It's called Array Generator. It will just create arrays for us. I'm going to use a particular one, and we can talk about that choice in a sec. So if you, I can talk about it now. If you think about the solution we just went through, it'll perform very well if the max is at the beginning of the array, but it's going to do more work if the max is at the end of the array. So I'm actually choosing a sorted array where the max is always going to be at the end. So we'll just see. It is the worst thing we could do for that algorithm. Okay, but first we're going to try it on my initial bit of code and see what kind of performance we're getting. So let's just run this. And what it's printing out here is the size of the array that's in, the absolute time it took. This is the in seconds, how much time it took to do the max function. And then the ratio of this time to the previous time. So what's the ratio? And note that if an array is twice as big, we would expect it to take about twice as long because we have to do about twice as much work. And in fact, you can see this is borne out here. For an array of 500 million elements, I'm taking half a second, whereas for 250 million elements, I'm taking 1/4 of a second. Okay, and you can see that the ratio here is close to 2. Note that there's a little bit of noise here, and this is just because there's systems effects and other things running on your machine. The noise is very noticeable when you're at small numbers. Small numbers essentially take no time. And so in order to see these kind of performance differences, you need to get large enough arrays where it's taking enough time that you can actually measure it in a meaningful way. So you'll get noise like, here 4, here you get 1. But as things get large enough, usually you'll see some sort of pattern. So this makes sense. About twice as long for twice the size of the array. Let's try this other solution that we have as a candidate and see how it does. So here's my solution where it doesn't indent very nicely here. Let's fix that. Okay, this is the solution where we're determining at each point whether or not we have found the maximum element. So each one, we're just checking it against all of the others. And let's see how it performs. And, oh, this is very different. I believe I had, what, half a billion in half a second? And, oh, wow, I'm up at, wow, 10 seconds just for 128,000 elements. That's not great. So this shows you the kind of performance hit you can get if you write code in an inefficient way. Note that for small values, it probably doesn't matter here. If I had 1,000 elements in my array, who cares? It's going to take not very much time. But by the time we're getting up to arrays of even less than 1 million, this is a quarter million. I haven't even computed it yet. You can guess how long you think it might take based on the kind of numbers you're seeing. You can see it's about 4 times as long every time. And indeed, this is borne out. So it took about 10 seconds to do 128,000. So it's going to take about 40 seconds to do 256,000. So each, for an array twice as big, it takes 4 times as long. So if you remember your high school trigonometry, if you plot that function, you're going to end up with a parabola, quadratic equation. So this is quadratic growth in terms of time on an array. And so this is an objective criterion where you can say, oh, this solution is worse. In fact, there are people that say this is not a solution at all. This is a bug. This is a bug that will show up at some point if you end up getting large enough input. So performance is an important measure or metric for determining the quality of code. Okay, so in conclusion here, when you're reading and writing programs, you need to think incrementally. We think in small steps. That's how the computer works. And so in order to program it, we have to atomize our thinking down to these fine-grained steps. And this, of course, this is the key to being a programmer, is being able to think in terms of making small amounts of progress. We saw how to do that with loops in particular. Loops are very important for programming because almost all programming is done over repetitive tasks. The way you think about loops is using invariants. And they're sort of a key to understanding loops. Even if you're just using them implicitly, they are the key to making progress as a programmer. And finally, performance really does matter. So we're not talking here about, oh, this is just a little faster, a little slower. No, we're talking about dramatically different performance for 2 apparently sort of similar quality solutions. So in this class, we will be emphasizing the correctness of our solutions and the performance of our solutions.